remind you of where we were at the end of Monday. We were building up this kind of vector data type, which was kind of like a dynamically allocated array, and it was using those dynamic memory allocation functions. But what was different about it is that we had a structure that allowed us to keep track of that pointer, as well as sort of storing the length information as well. That allowed us to build up a series of functions that we could use to either create the array, create the vector, resize the vector, and also kind of arbitrarily either remove things from the vector or insert things into the vector at a given location. We built up most of those functions on Monday, and we just had one remaining. And it was kind of similar to the insert function in terms of what we have to do, sort of like the converse operation. So if we go back to what we did for the insert vector function or vector insert, we just recognize that sort of similar to what we had previously done with our like array swap and sorting functions, we had to recognize that we were kind of just copying a one by one element. We want to get what was the last element, we want to move it one along. What was the second to the last element, we want to move it one over. So we just have this loop that basically starting at the very end, working our way back to the place where we wanted to insert something, copying from one value to the next value. For the remove operation, it's going to be quite similar. We want to just remove the value at that location. So it's also going to be a series of just basically copy operations of vector dot values. The main difference here is it's okay if we actually overwrite the values as we go. We're not inserting something new into the vector. We're kind of removing a value from the vector. We could have written a version of this that actually returned the value as an integer and return that back to the function. But the way it was spec'd out, we just said, given a location, remove that value at that location. And so here, we don't have to be nearly as careful with regards to how we order that for loop. In the insert example, we wanted to make sure if we went from location up to length minus 1, we'd actually be copying the same value over and over and over again. In this case, there's no harm associated with this. We're just taking the next value and moving it into that next location. So we can start directly at that location that is being specified. Again, it's being called at the very bottom here with location 3. So that would be index or offset 3 into the dynamically allocated array. We would start there. We would go to length, but because we're kind of copying the next one over, we can go to length minus 1. We'll see why that we would want to do that in just a second here. And we're doing something very similar. We're saying not vector.values of I is vector.values of I minus 1, but vector.values of I equals vector.values of I plus 1. Take the next one over and move it to the current location. So when I is equal to vector.length minus 1, we're taking what was, and it never gets it when it's I minus 2 or length minus 2, we're taking what is it currently location, length minus 2, and give me the value of length minus 1. So we take every element, we copy it, you can think of it to its leftmost element, and then we do need to make sure we have that function that allows us to resize our vector. When we inserted something, we're growing the vector by 1. In this case, when we are removing something, we're removing the vector by 1. Now, that function for resizing is the one that's actually doing the reallocate call, right? That's doing the dynamic memory reallocation. And in this case, potentially, if we made it longer, we're initializing to 0. Whether or not in an actual real-world implementation of a vector class, whether we'd actually want to resize by 1 every time we want to insert something or not, it's an implementation decision. It's not that clear we would necessarily want to, because this can be a pretty expensive operation, allocating new memory, keeping track of the data structure that stores where things need to be on the heap. What's probably a more likely outcome would be when we recognize that we don't have enough space in the vector, maybe we allocate twice as much space or an extra 100 elements of space. And only when we run out of that space do we then go and do a memory reallocation, because it's going to be considerably more expensive than doing this just this for loop that's copying operation. We can run it to confirm that it still works as expected. So we had 15, we inserted. We now remove an entry at location 3, that's 0, 1, 2, 3. We remove that value of 77, and it does kind of work. And we have, now that we've written this function, kind kind of a nice dynamic memory structure, this data structure we can use, where in terms of our usage of it, well, we have the print function. We just have to think about, do I want to insert something in a location? Do I want to remove something at a given location? Do I always want to resize the entire thing at any given point in time? And we have this dynamic memory allocated array where we really don't have to be so strict in our thinking in terms of what size it needs to be. We resize it as we need it. We insert things at whatever locations we want to. And that's kind of the value of a higher level language that allows us to think about data structures versus just thinking about pointers and memory. It's not the same as a C++ vector class, because that one also can be templated to be a vector of structures or a vector of floats. It doesn't have to be ints like the one we just created here, but conceptually it's very similar. It's, okay, I know I need some contiguous region of memory. I don't want to have to really think about the management of it, but I want all the advantages of having this dynamic memory allocation, this dynamic memory structure. And that's one of the values of having this structure and pointers within this structure. The downside, beyond just all these calls to the memory allocation functions, is that resizing, that inserting, that removing functionality. It doesn't seem bad in some sense. Just a little for loop we're adding that we're copying all the values. We're shifting things either over by 1 to the right or shifting things over by 1 to the left. Doesn't seem like an inefficient or a quote unquote bad thing, but it probably is from a formal evaluation of this data structure, in that every time I want to insert or remove something from this vector, I have what's considered an order big N, this linear operation. The time it takes to insert or remove something from this vector is a function of the entire size of the vector. If the vector is of size 16, well, who cares? Or 17, who cares? If the vector is of size 17 million, we start to care. It becomes a very expensive thing to then insert or remove something from that data structure. Here, I mean, it's expensive in terms of runtime, the amount of time it takes to actually do that removal operation. Again, it's just a for loop, so it doesn't seem like much to us. But the length of that for loop, the amount of times that for loop iterates, is a function of the length of that vector. If it's 16, if it's 17, if it's 110, who really cares? Is that really going to be critical for performance? But if it is 17 million, 110 million, the kind of thing we may want to have a custom data structure to support, that's going to be a very slow operation. That's really you're going to really feel the pain of doing those insert and remove operations. There are many different alternate data structures, and there's whole classes on data structures you eventually could have the opportunity to take. One such data structure that allows us to ameliorate that specific issue of having to traverse the entire thing, and traverse is a bit of a formal word, but we have to kind of loop through the entire vector. One such data structure that ameliorates that particular problem is referred to as a linked list. Has anyone heard that term before, a linked list? Okay, a couple of you. It is almost a stereo or typical or cliche interview question if you are applying for a software programming job, which is, well, how do you go about sorting a doubly linked list? And it's a cliche because it's not terribly interesting, but it's meant to be a test of, did you take enough programming courses, even for double E's, even for a position where you don't think of yourself as a software engineer, that's not your major, but it's very likely, as we talked about on day one of this course, that your first job or your entry point to the workforce could be as a development position. It is the kind of job that even you would be expected to support. We'll talk a little bit about this linked list structure. We'll create one. We won't do the actual sorting, although we have what we need to be able to do the sorting as well. From the C programming's perspective, the idea of a linked list is we don't have, unlike in the vector, a pointer to this array of values. We're going to be a little bit clever, maybe hackish, depending on your perspective, with the syntax. And as part of the data structure itself, as part of the struct, we're actually going to have a pointer to that same exact type itself. It's kind of self-referential. It's not quite recursive, but it's a pointer to itself, or a pointer to a variable of the same type as itself. Let's look at what we're doing here and why this actually works. It's a little bit of maybe chicken and egg. Self-referential is probably the right term for it. As we're defining our structure, here I'm calling it int node. So this is a node in our list of integers. It has a value, so a single value is going to be stored per variable of this structure type. And as part of it, and you can see the syntax here, we're going to have a struct int node star, a pointer to a variable of that same exact type that we are currently creating. which I think is a little hard to wrap one's mind around, except when we just recognize that a pointer is nothing else than a variable that stores an address in memory. We need to know in C at least the type of thing we're pointing to. So when we do pointer plus plus, we know what that means. We mean we're going to the next structure. But that's really the main reason why we have to have a typed pointer in the language. So all we're saying here is each variable in our dynamically allocated array of these variables is going to have the actual value we're interested in, the integer that stores whatever we're interested in storing, and it's going to have a pointer to point to the next thing along the line. Here, when we had the vector, it was this contiguous allocation and reallocation. Give me 15 integers. No, actually, I want 25. No, I changed my mind. I want 24. We're calling those malloc, realloc functions to grow and shrink that array of memory at a given time. That was nice and simple. The downside is what I was trying to show in this code. As you get 17 million elements, it's quite inefficient. Here, when we have our structure that is pointing directly to what the next element is, we no longer have to have all of these elements be contiguous in memory. They can be wherever they need to be at any given point in time. Visually, it looks like something like this, where we define a particular pointer to refer to as the head of this list. So we would allocate a pointer in the first place. So we would allocate a single node, call it the head, give it a value, point it to nothing in the next. So we have a value. And then as we allocate more as we go, every time we allocate another one of those elements, we set the value. We still have to do the dynamic memory allocation. We allocate a new element of this type, and then we set the pointer to be whatever we happen to be pointing to next. That's different than the array. While you could also visualize the array as kind of looking like that, in practice, the array is this contiguous block of memory. In practice for the list, this could in fact be contiguous in memory, but it no longer has to be. I have for each of these elements, and these are separate values. This first value is 1, this is 17, this is 23, this is 6. Each of those then also has, as part of what's allocated for it and what I as the programmer now have to explicitly set up, this linking of prior element to next element, or prior node to next node in the list. I don't show the code to do that yet. We can play around with the code to do that at the rate we're going probably on Monday, but we can still do so. That pointer, and that's what that arrow is meant to indicate, right? The pointer is just a variable that is part of the structure, and by default, if there's nothing else to point to, we just set it to null or something. It's a null pointer. But as we create a new one, we started with the first one, we now create a new one, I point this node's next pointer to that next structure. So when it comes time to, let's not worry about sorting for now, but when it comes time to insert an element into that list or remove an element from that list, again, for the vector, we had to go through a for loop and just do an explicit copy of everything over. For our linked list, if I want to remove this element here, all I really have to do then when I want to remove this particular element here, well, I should probably delete it. So probably still a free operation to get rid of the storage associated with it. I have to get rid of it, and then I have to take this pointer, which was previously pointing to it, and just move it along to the next one in line. I'm changing an address being stored in this element to say, hey, next is not this one here, we're removing this one, next is this one over here. And same for inserting, although it's a little bit harder to visualize because the slide is kind of full here. Well, if I want to add something to the very end, I allocate a new node here, and I make sure this next points to that element there. So in inserting, removing, appending, removing, popping something off the top, it can be done in constant time. It's going to be the same number of operations no matter how big the linked list is. For accessing an arbitrary element, it's going to be slower than the vector, because now you can't use that array syntax where you do values of 7 or values of I, because this is not guaranteed to be contiguous in memory anymore. Once I remove something and add something over here, they're not located next to each other in memory anymore. The order they are in memory is something we can't predict, we can't guarantee. When I want to grab the 7th element in this linked list, I got to start at 0 and go 0, 1, 2, 3, and follow them all the way along. At least though, while that part may be slower, it's always going to be the same amount of time. And the performance of inserting and removing things has no indication on the actual size of the list itself. We can do kind of an arbitrary insertion in a constant time here. When it would come time to sort it, and I don't think we'll write the code to do sorting a linked list here, it'd be very similar to our array code. Doubly nested for loop, if we want to use that algorithm at least. A doubly nested for loop, comparing if this value is greater than this value, and if so, swap them. The only thing we change in our code is that swap logic is now no longer using the array syntax. The swap logic would be using this pointer syntax. Point this one to this one, point this one back to this one, and point this one to the next one, so that those nodes are then in reverse order from what they previously were in memory. The cliche interview question is, how do you sort a doubly linked list? The only difference there in a doubly linked list is you have these pointers that point to the next one. That's the single linked list. You also have pointers that point to the previous one. So they go in both directions. You have a little arrow that goes to the next one in the list, as well as an arrow that goes to the previous one in the list. So when you do that swapping operation, there's a lot of arrows you have to rewrite. That's basically the only difference in sorting this versus sorting anything else. Let's at least get started with what an implementation of that would look like. It would start at some point with that kind of self-referential definition of the structure itself. Each node in the list is going to have a value associated with it, and it's also going to have, and we have to use that struct syntax because we haven't defined the actual int node yet at this point in the code, a pointer to an element of the same exact type. Struct int node is exactly the same as int node t here. We just haven't defined int node t. We're in the process of defining int node t at this point, so we have to use that struct syntax here. The rest of the code I have in this example is meant to illustrate using the curses library to print things. For Lab 8, how many of you have like the animated print hello world example working where it's wobbly and rotating? I see two, so I'll give you each half, so that's 1, 2, 3. Okay, well, that's not enough. We need all of us to get to that point. This example would not do all of the things we would need in our Lab 8, but we can get started with it. Curses is an alternate way of formatting how we want to print things to the screen. It is significantly more powerful than just doing printf and the like, but there's just a little bit more setup required for it. For me, when I'm writing programs that I think might be using curses, I like to abstract it a little bit and leave myself a pound define. This is my own definition to say, yeah, I want to use curses, or it's a mess for me right now. I'm going to turn it off and switch back to printf. So ignoring that part at least, right now, there's an initial like screen setup one has to do. You're saying, I'm going to be printing to this terminal, this shell terminal, and there's a million different possible settings one can apply to that. This would be a function. You don't have to wrap it and call it print setup, but that makes it easy to kind of separate out and knit the screen. Get started with curses mode. Turn off the actual cursor itself. Depends on what your needs are. Sometimes you want the cursor to be there and flashing. In this case, we don't need it necessarily. I forget what raw mode means. We don't buffer our input, so if someone presses a key, that key stroke is immediately available. No echo would be when a user presses a key, it's not like scanf, you don't actually see the letter being pressed on the screen. So if you want to build a menu for your project and you don't want someone to see the WASD that you're typing in, you would turn on no echo. That would be something you would call, for now at least, all 4 of those functions at the beginning of every one of your curses programs. It's less important, but if you want to be able to use your shell when you're done, you want to call end win at the end of your program. Otherwise, that's pretty much it. And instead of then calling printf, let's get rid of that stuff because that's not super useful. Instead of calling printf, you'd be calling this mv. There's several different ones you can call. mv printw function, which is very similar to printf. In fact, there's 2 inputs we'll talk about, but you can print hello world. And it kind of does what you expect. As part of that, you pass it a location in which you want to do that print. If you remember back in our playing card example, we didn't use curses, and we had to kind of manually print stuff. Like, I want to print this line of this card, then this line of this card. We were able to get it to work by just carefully sorting and organizing our printfs, but it was pretty painful, right? In this case, if I want to print something at a location, I just tell it the location I want to print it at. And I broke it. Let's leave things here for today. I know exactly what I did. It's because it's in that loop and it's not sleeping. And I didn't actually tell it to draw. So on Monday, please come on back. We'll go through at the very least a curses example so you feel more comfortable finishing up that example next week in lab. And we'll learn about linked lists as well. Okay.